Volumes of revolution, disk and washer method. We will be rotating about vertical lines of the form x equals b, or with respect to y. Objectives. By the end of this lesson, you should be able to identify the region being rotated, ensure you are rotating about a vertical line x equals a, find the limits of integration that must be y values, determine if you will need the disk or washer method, and set up the integrals with respect to y needed to find the volume of the solid. Let's start by looking at the formula for the volume of a solid of revolution using the disk method when our cross sections are perpendicular to the y-axis. Now, a lot of this is going to be familiar. There's only some slight differences when we're rotating around a vertical line this time. We're going to need our function to be in terms of y, so f of y is going to need to be continuous, and f of y is going to need to be greater than or equal to 0. So a function in terms of y is positive when the region is in quadrants 1 and 4 this time. And we're going to need our function to be defined on y values that extend from c to d. So our function limits of integration, are going to need to be y values. So let's stop and look at this image on the left. We'll go ahead and say that this is the function f of y, this line here, and it extends from y equals c, so we're looking at the y value here, to up here, y equals d. And we're rotating around this vertical line here, so the y-axis is a vertical line of the form x equals 0. So then the volume obtained by rotating the region between f and the y-axis about the y-axis, so again x equals 0, is given by the following formula. So let's just take a look. What we're doing here is we're rotating around this y-axis, so our cross sections are going to end up being circles. I'll just sort of try to draw one out. And this is going to be a disk, so there's no hole that we're carving out of the middle. So the cross section, the area of the cross section, the formula for a circle is pi times the radius squared. Well, the radius needs to be a function of y, and we're going to obtain the radius by doing right minus left this time. So in this example, right minus left, the right function is f of y, and the left function, this vertical line here, is the line x equals 0. So f of y minus 0, well, that's just f of y. So this formula should look familiar. Really, the only difference is that our limits of integration are y's. My function is in terms of y. And of course, I'm integrating with respect to y. So big R of y equals f of y. That's the radius of the circular cross-section for different values of y. So we can see this would be the completed solid, the solid of revolution obtained by rotating around the y-axis. And now we can also apply the washer method when our cross sections are perpendicular to the y-axis. So for the washer method, we're going to need two functions in terms of y, f of y and g of y, that are continuous. And f of y has to be greater than or equal to g of y, which means to the right of in this case. So we're not looking at above and below, we're looking at right and left. So f of y is on the right, g of y is on the left. Both of them are greater than or equal to 0, so in quadrants 1 and 4. And we're going to look at these on the y values from c to d. So let's just kind of try to draw an image here. Let's say that, I'll try to use different colors. Let's say this is my function f of y, and it's on the right hand side. And then let's say this green one is my function g of y, and I'm interested in rotating around the y-axis again, or in general, just I'm rotating around a vertical line so that my cross sections are perpendicular to the y-axis. So the volume obtained by rotating the region between the graphs about the y-axis x equals 0 is going to be the integral from c to d of pi times the big radius squared minus pi times the small radius squared. So c and d, we can label those values. They are going to come from the y-axis, so these points of intersection here. So the top one will be d, the bottom one here will be c. So our big radius is going to go from the axis of rotation to the further away function. So there's my big radius. And then my little radius will go from the axis of rotation to the closer function, to the green one. So right minus left, in this case, the right function is the blue one, f of y. So f of y minus, this line was x equals 0. So f of y minus 0 is right minus left, and that quantity is squared. And then little r is the green function g of y minus 0, and that is all squared. And of course, just subtracting 0 doesn't do anything, so we just have f of y squared minus g of y squared. So again, this should look familiar when we rotated around a horizontal line. So now we're rotating around vertical lines. So cross sections perpendicular to the y-axis, just to put a little note for ourselves, it means that we're rotating about a vertical line, is what we're trying to generalize here, as opposed to horizontal lines like the x-axis. So now the recommended strategy for when the washer method is needed. First, we start by drawing a line from the axis of rotation to the function furthest away and label that line big R. Then, draw a line from the axis of rotation to the function closest to the axis of rotation and label that little r. So big R meaning big radius, little r meaning little radius. So this should look familiar. Until the third step, find the length of each line, big R and little r, using right minus left. So this time, because our functions are in terms of y and we're rotating around vertical lines, we have to use right minus left to find the length of the radii. And our functions must be in terms of y. So they will not always be given in terms of y. We might need to solve for x equals so that they are functions of y. And then the limits of integration must come from the y-axis, so they must be y values. And at times we might need to find points of intersection, and they again must be y values. And then note, just like for when rotating around a horizontal line, you may have to split the problem into two separate integrals if the right and left functions switch over the y interval, or when trying to find the big radius and little radius, you notice that if you choose one point, you may hit one function, but if you choose another point, you may hit another function. You'll have to split it into two separate integrals. All right, let's start with some examples. Calculate the volume V of the solid obtained by rotating the region between y equals x cubed, y equals 1, and the y-axis about the y-axis. So first we're going to need to draw the region. So the region is bound between y equals x cubed. So let me go ahead and draw an xy plane here. Y equals x cubed looks something like this. It's one of the basic functions. We should know what the graph looks like without a calculator. Y equals 1. So y equals 1 is an example of a horizontal line. So I'm going to draw a horizontal line at 1. So let me label these for now. This is y equals x cubed. This is y equals 1. And the y-axis. So it's bound by the y-axis, which has already been drawn. So now let's indicate the region that we're going to try to rotate. So it is this region right here that we are rotating about the y-axis. So I'm using this symbol to indicate that's what I'm rotating around. So this is the region that intersects all three lines. So the horizontal line y equals 1, the curve y equals x cubed, and the y-axis. So that is the region bound by all three functions, and it's being rotated around the y-axis. Now, since the entire region borders the axis of rotation, so the entire region is right up against this line, if I were to draw a cross-section just to understand what this looks like, that would be my radius, and I would rotate it all the way around. So I would have a disk or a circle. So in other words, the washer method is not needed. The disk method only is what is needed. So the formula here for the volume is going to be V equals, the pi is in the front, the integral from. So I'm going to stick in the habit, and I want you to as well, to label your limits of integration with either x or y to keep it straight for when we have to enter an integrand and we want to make sure all the variables match. So the smallest y value of my red region here is 0. So from the y-axis, my lower limit of integration is y equals 0. And my upper limit of integration, well, this region stopped at y equals 1. So my upper limit of integration is 1. And so now my radius, the radius at any particular point, is going to be given by right minus left here. So the right function is y equals x cubed. Now this is where we need to pause, and this is exactly why we label our limits of integration as y's, because if I were to put in my right minus left as x cubed minus 0, I would be incorrect. I need my function to be in terms of y. So I need to rewrite this function y equals x cubed so that it's x equals some function of y. So to isolate x is being cubed, so I'd have to take the cube root of both sides. So x is the cube root of y. So the right function here, this portion on the right, is the cube root of y, and the left is 0. So it's the cube root of y as a quantity squared. So technically it was minus 0, but I'm not writing out that part, and then dy. So in getting in the habit of labeling your limits of integration as y's and including your differential dy, it will hopefully remind you that you have to rewrite the function as a function of y. So this here is my f of y, or my big R of y, my radius as a function of y. So now this integral wouldn't be difficult to solve by hand, but the focus for right now is going to be the setup of these volumes of revolution. So I'm going to stop right here. This would find the volume of revolution for this region about the y-axis. Alright, in this next example, calculate the volume V of the solid obtained by rotating the region between x equals y squared and x equals 4 about the a y-axis, b line x equals -1, and line x equals 3. So it's 3 separate problems, but we're rotating the same region every time. So let's draw that region. I'm going to draw my xy plane here. And x equals y squared. So right now we're starting off by graphing a function that's already in terms of y. So it's an x equals function. So if I were to graph y equals x squared, of course it would look like a parabola going through the origin. So this is the function y equals x squared, but I want to graph x equals y squared. So notice that y equals x squared is in quadrants 1 and 2, where my y values are positive. So if I were to graph x equals y squared, I want my function to also be positive, but when I'm in terms of y. So that's going to happen in quadrants 1 and 4. So it's like I'm going to turn this parabola on its side. So this is what x equals y squared is going to look like. And then the line x equals 4, well, that is a vertical line at the y value 4. So I'm just going to go ahead, the x value 4. So I'm going to go ahead and draw my vertical line at x equals 4. And then this parabola here is x equals y squared. So the region that I am interested in is this one here. So this is the region of intersection between these two functions. Now part A says rotate that region about the y-axis. So for part A, my axis of rotation is going to be the y-axis, this one here. And so if I think about rotating this region, I am going to need a washer method. So what tells us that is if the entire region isn't bordering this axis of rotation, then I'm going to need a washer method. So right now, only this one point at the origin is the only one touching this axis of rotation. So everywhere else, there's going to be a big gap. So if I think about rotating this region, let me just pick a particular value. So I'm rotating it between this y value here, which we're going to need to find, and this y value here, which again we're going to need to find. We're rotating this region around the y-axis. So let me go ahead and attempt to draw what's happening. So this region, this one slice, is going to spin all the way around. So let's see if I can attempt to draw it. This is going to be one cross section. So one cross section is going to look like a washer. So if I spin this thing around and I end up with my final solid, it's going to look like an hourglass shape, which obviously is going to have a giant hole in it in the middle. So I am going to need the washer method here. I am going to have a big radius and I'm going to have a little radius. So to start my problem, volume equals pi times the integral from, so I need those y equals values. And to find them, I need to set my two functions that are intersecting equal to each other. So my two functions are y squared, so x equals y squared, and x equals 4. So I'm setting y squared equal to 4. So y squared equals 4. If I take the square root of both sides, I get y equals plus or minus 2. So down here, y equals -2. Up here, y equals 2. So those are my limits of integration, and I will label them as y equals value. So y equals -2 to y equals 2. And so now I need the whole big radius and little radius concept. So I'll change colors here. My axis of rotation was the y-axis. Now, I don't want to choose 0. That is not the one point that I want to choose to find a big radius and a small radius, because in both of those cases, the big and small radius is 0. But I can choose any other point between -2 and 2. So I'm just going to go ahead and choose a point right here on the bottom, and I'm going to go from the axis of rotation to the furthest away function in my region. So my region was this one here, and from the axis of rotation to the furthest away function that we're dealing with in the region, that's x equals 4. So now that's big R, and little r goes from the axis of rotation to the closer function. So that one stops at this curve, which was x equals y squared. So now what goes in my washer method formula is the big radius squared minus the little radius squared, and each one needs to be squared separately. So big R is right minus left, so 4 minus 0, and little r is right minus left, so little r, this curve here, is x equals y squared. So this is nice. My function's already in terms of y, so it matches the variable of the limit of integration, minus 0 dy. And so, of course, we didn't need to write out the 0, so now it's just pi the integral of. Now that we've assured ourselves everything is in terms of y, there's no need to write out the y equals again. So this is 4 squared, or really 16, and then y squared squared, which, of course, is y to the 4th. So, again, the focus today, though, is on the setup. At this point, solving this integral by hand wouldn't be too tough. Or we can enter it into our calculator, would be even easier, but the point is the setup is what matters. So now let's take a look at what would happen if we rotated about the line x equals -1. Alright, I've went ahead and redrawn the region so that now we can focus on the line x equals -1 as the axis of rotation. So x equals -1 is over here, and let me go ahead and draw the axis of rotation now. So we're spinning around this vertical line. And this one's definitely going to be a washer method. So here's my region over here, the one outlined in red, and no part of this even touches the axis of rotation. So that definitely means we're going to need a washer method. So only when the entire region borders the axis of rotation do we not need a washer method. So right now we are going to have a big radius. So starting from the axis of rotation, go to the furthest away function that is part of the region. So the furthest one away is x equals 4. So there's big R. And then from the axis of rotation to the closer function, that would be the x equals y squared function, so that's my little r. So setting up my integral needed to find the volume, I'm going to have pi times the integral from, my region is still from -2 to 2 on the y-axis, so y equals -2 to y equals 2. And my big radius, right minus left, so remember that this vertical line is x equals -1. So the right function is 4, so 4 minus the left function is -1 squared. And then minus the little radius squared, so little r was here. The right part of little r is on y squared, so already a function of y, minus the left function is -1, so minus -1 dy. So if we wanted to simplify this a bit, it's pi times the integral from -2 to 2 of 5 squared, so 4 minus minus 1 is 4, or so 4 minus minus 1 is 4 plus 1, so 5, and then minus y squared plus 1 squared dy. So this is the integral needed to find the volume of the solid rotated now around x equals -1. Finally, in looking at the last problem that was rotate around the line x equals 3, I made a typo. So let's talk about why I made a typo, just to take a learning experience out of this. There's no way I could rotate this region about the line x equals 3, because now my axis of rotation is right in the middle of the region that I'm rotating, which doesn't quite make sense. So that was just a typo. It was supposed to be x equals 4. Let's erase that. So I'm rotating this region here, the same region, around this line here, x equals 4. So what's unique about this problem is that my region does entirely border my axis of rotation. So that means I only need a disk method. So let's just draw one of the cross sections here. So I'm going to have a radius. So from the axis of rotation, and that method still works, I start from the axis of rotation to the furthest away function. So now this is my big R. And from the axis of rotation to the closer function, well, I'm right on top of the closer function, so the little radius is 0. In other words, there's no need to use a washer method. There's only disks that look something like that. Sorry, it doesn't look too great, but it's just a circle, or a disk is going to be each of the slices of my cross section. So now let's go ahead and set up the integral. So the volume is going to be pi times the integral, still from -2 to 2, so that hasn't changed. So y equals -2 to y equals +2. And we're only going to have a big radius this time, and we still obtain the big radius doing right minus left. So the length of this radius, the right function is 4, the left function is y squared. So 4 minus y squared is big R, and of course we need to square big R dy. So this was a disk method only because the entire region, the red part, completely bordered the axis of rotation. So in the first example, when we were rotating around the line x equals 0, or the y-axis, only one point touched the axis of rotation, but the rest of the region was far away from the axis of rotation, meaning there was going to be a gap involved. So if there's any type of gap, that gap indicates the hole in the washer, meaning we're going to need a washer method. So this is the integral needed to find the volume of revolution when rotating around x equals 4. Alright, next example, calculate the volume V of the solid obtained by rotating the region bound by y equals x, y equals 4 minus x, and the y-axis about the y-axis, and then about the line x equals -2. So let's go ahead and draw our region. Our region is bound by y equals x. So y equals x is the line that goes through 0 with a slope of 1. Definitely a basic function we should know how to graph without a calculator. Y equals 4 minus x. So this is a line with a y-intercept of 4 and a slope of -1. So it is going to have a negative slope, of course, and go downward. It's a linear function. So this is what 4 minus x looks like. And it's bound by the y-axis. So the y-axis is already drawn for us. So in other words, the region, let's go ahead and try to outline it in red here, is this, whoops, missed it a little bit, but this triangle is the region that I am rotating first in part A about the y-axis. So you'll notice that the entire region borders the axis of rotation. So we are going to need a disk method. So there's not going to be this hole carved out of the center. We only need the disk method. However, the disks are going to need a radius that extends from right to left, and depending on where I pick my radius, so my limits of integration are going to go from 0 to 4. That's where this region extends from 0 and then up here till 4. But the problem is that if I pick a radius, so let's say right here, the right function is y equals x, and the left function is this line x equals 0. But if I pick this to be my radius, so this line up here, now the right function is, I should have labeled it, 4 minus x. So this one down here is 4 minus x, or this line with negative slope. So now right minus left would be different. So that indicates that I need to break up my integral to find the volume into two separate integrals. And I need to stop at this point of intersection, whatever this y value is. So where do 4 minus x and x intersect? Well, if I were to set these two functions equal to each other the way they are, so let's talk about that. If I were to set x equal to 4 minus x, my answer would then be an x value. And I don't want the x value where they intersect. I want the y value where they intersect. So, in other words, what I need to do, and I'm going to need to do it anyways, is solve each of these for x. Well, if y equals x, then x equals y. So this one is already solved for x. But this one, if I want to solve it for x, I'm going to get that x equals 4 minus y. So if I add the x to the other side and subtract the y, that means this negative slope function is x equals 4 minus y. So now I want to set those two equations equal to each other. The y equals 4 minus y. So add the y to the other side, I get 2y equals 4, so y equals 2. So that middle point is 2. So my two integrals, the limits of integration, will go from 0 to 2 and 2 to 4. Alright, so let's get started writing part A out. So volume equals pi times the integral from y equals 0 to y equals 2. So right now, I'm just looking at rotating this little triangle right here, which again only requires a disk method, so the radius is right minus left. The right function, this line here, is just y. So y, and then the left function, so right minus left, is 0. So y minus 0, quantity squared, dy. So this first integral finds me the volume of rotating this blue triangle around the y-axis. And now I need to rotate the top triangle around the y-axis, so that one, I'm going to need to add it, plus pi times the integral from y equals 2 to y equals 4 now. So my limits of integration on the y-axis go from 2 to 4 on this triangle. And the right function, this purple function with a negative slope, is 4 minus y. So 4 minus y, technically minus 0, that's the left function, is minus 0, quantity squared dy. So this is now the integral, the two integrals it takes to find the volume of the solid to rotate this region around the y-axis. And now let's try rotating around the line x equals negative 2. So now I'm moving the axis of rotation left, so I'm rotating around negative 2. So this one is going to require a washer method. And I'm still going to need to split it up into two integrals, because if I go from the axis of rotation to the furthest away function, the furthest away function is going to change depending on where I pick from the axis of rotation. So if I were to pick up here, the furthest away function is now this downward line, this negative slope line. And if I were to pick over here, now it's this positive slope line. So I'm still going to need to break it up into two integrals. So for part B, the volume is pi times the integral from 0 to 2. So nothing changes about that middle point where they intersect. But now there's a big radius. So the right function is y, and the left function is negative 2. So y minus negative 2 squared, there's big R, minus, so now there's also a little r. In my washer method. So right minus left here, the right function is 0, and the left function is negative 2. So 0 minus negative 2 squared, dy. So this finds rotating this bottom triangle around the line negative 2. So there was clearly a washer method, because this little black triangle doesn't border the axis of rotation, which moved way over here. So there's a big radius and a little radius. And so now I need to add, and I'm not going to have space to move to the right, so I'm going to need to add the integral from 2 to 4 on the y-axis. And this one's going to have a big radius, big R, and a little radius, little r. So the big radius, sorry, my line keeps hiding in the back. So my big radius is this function here is 4 minus y. So 4 minus y minus the left function is negative 2. So minus negative 2 squared. And then minus the little radius right here. So right minus left, 0 minus negative 2 again, squared dy. So these are the unsimplified versions of writing this. If I wanted to make it a little more compact, I could say pi times the integral from 0 to 2 of y plus 2 squared, and then minus 2 squared, or 4, right? Plus, minus is plus, so I have plus 2 squared, which is 4, and then plus pi times the integral from 2 to 4. And then here on the inside I have 4 minus y, and then this is plus 2, so 4 plus 2 is 6. 6 minus y squared minus 2 squared dy, or you could have just written 4. So now, again, at this point, it was just about the setup. We could solve this by hand very easily. I mean, we would have to distribute this as y plus 2 times y plus 2 if we did this by hand, because, of course, this squared does not distribute, so this is not y squared plus 4. This is not 36 minus y squared. We'd have to do 6 minus y times 6 minus y in the distribution if we did this by hand. But the important part here at this point is the setup. So understanding that we would need to break this up into two separate integrals to find the volume. Alright, in the last problem, calculate the volume V of the solid obtained by rotating the region between y equals e to the x equals 2, the y-axis, and the x-axis about the y-axis. So let's graph our functions here. That's not very even, but we have y equals e to the x, so it's this increasing function. We know that it goes through 1, so this is y equals e to the x. X equals 2, that is a vertical line at 2, so x equals 2. And we're bound by the y-axis and the x-axis here. So let me highlight my region, or outline my region in red. It is this one here. So that's bound by all 4 of my functions. So e to the x equals 2, the x-axis, and the y-axis. And we're rotating this thing about the y-axis. Alright, so now let's take a look at what we have. We have a portion of our graph that entirely borders the axis of rotation. So this portion right here borders the axis of rotation. So this part from 0 to 1 is not going to require a washer method. The portion from 0 to 1 is only going to require a disk method. So we can draw one of our cross sections here. It's going to be just a disk. But if I were to go from 1 to whatever this point is, and we're going to have to find that point up here, that y value, when I extend from 1 to that number, I am definitely going to have a washer method. So if I were to draw that, it just gets kind of tricky to draw, but I'm going to have a washer that extends over here. So this top part is going to require a washer method. This bottom part is going to require a disk method. So let's start by setting up the formula for finding the volume of this bottom region. So I'm going to extend from, so start with pi times the integral from y equals 0 to y equals 1. And here my radius is going to be right minus left, so there's only one radius. The right function is 2, the left function is 0. So it's just 2 squared dy. So this part here finds rotating this region around the y-axis. Now we need to focus on how do I find the volume of this top part from 1 to whatever number this is. So let's try to figure out what this top number is. This top y value is going to be where e to the x and x equals 2 intersect each other. But there's a real easy way to think about what this y value is going to be. If I plug 2 into e to the x, that will give me the y value. So in other words, this coordinate point, let's think about that, is 2 comma e to the 2. So the function's e to the x. If I have x equals 2, I'm just plugging 2 into that value. So the y value, the output here, so this isn't, sorry, I don't want to make it look like it's e e squared over y, this is the y value as opposed to this is the x value. So that means this upper limit of integration is y equals e squared. So let's start the second integral. So plus pi times the integral from y equals 1 to y equals e squared, which is just a number. And now I'm going to erase a little bit of the clutter here. So let me erase the actual cross section I drew earlier. So this was y equals e squared here. Alright, so we start from the axis of rotation and we go to the furthest away function here, and that's my big R. So the furthest away function is this line x equals 2. So big R is 2 minus 0. So that's what I'm going to go ahead and put right here, 2 minus 0 squared. So this is my big radius minus, so now my little radius from the axis of rotation to the closer function. The closer function is y equals e to the x. So this little radius is going to be this function minus 0. But I don't want to write e to the x because my limits of integration are y. So y equals e to the x. If I need to solve this for x, that means I need to take the natural log of both sides. So ln y equals ln e to the x. The ln and the e cancel. So x is ln y. So this right minus left here is going to be natural log of y minus 0. So ln y minus 0, quantity squared dy. So this is my little radius. So here's an example of where I would need, in the same problem, the disk method and the washer method when rotating around a vertical line. So my cross sections are perpendicular to the y-axis. They were a disk for the bottom region, and the cross sections were washers for the top part of this region. So this is the setup needed to find the volume of the solid when rotating this region around the y-axis.